here we were, if I'm not mistaken, given velocity time graphs. So, Tristan and Luis, the whole purpose of this section, it's just like the stuff we did before. We talked about position, then we talked about velocity, then we talked about position time graphs and how they relate to velocity, and then we did a bunch of acceleration stuff. We talked about those 4 kinematic equations. I derived 3 of them for you. And now we're going to start talking about velocity time graphs. Velocity time graphs allow us to do a few things. From a velocity time graph, given a graph for an object, we can start to find a few things. One of the things that we can find is the velocity. And just like before, if I gave you a position time graph and I asked you for position, you could just read it off the graph. If I asked you for displacement, then you were comparing 2 different positions. But again, you're still pulling that right off the graph. So for a velocity time graph, we're doing the exact same thing. We started by just pulling these things off the graph. So at 2 seconds, we were traveling at 30 meters per second. That's what this means. And we were going north, not Z. I have to read it like this. At 6 seconds, we were going, what is that, negative 10 meters per second, or alternatively, 10 meters per second south. And then we were talking about, I actually asked you, based on what you saw here, for you to talk to me a little bit about what the object was doing. And if I'm not mistaken, Zaid was walking us through a few things here. He said constant velocity, we were traveling at 30 meters per second, heading north, and then the object starts to slow down. The velocity is still positive, but it starts to decrease. At 3 3/4 seconds maybe-ish, we hit 0, which means at that moment, Zaid said the object stops. Velocity is 0. What's happening here? It's starting to go south. Yeah, and it's starting to go south, and it's doing what? It's picking up speed. So here we had, and notice along here, has the acceleration changed, or has the rate of my velocity changed at all? No, and how do you know that? Because the line is straight. And so nothing, as far as that goes, nothing's changing here. So we're starting to see some relationships for this kind of graph now, too. We've got, because this is constant, we know our object is slowing down, and now we know that it's speeding up, and it's speeding up at the same rate it was slowing down because this line is straight, which tells us something that's going to be important here. Based on this chunk of time, the slope of a VT graph, or velocity time graph, is going to be equal to what? The acceleration. Because the act of slowing down or speeding up, that word that encapsulates, I think is the word I want to use, that contains that concept, is acceleration. So the slope of a VT graph is the acceleration. So for this whole chunk, we can start using that language now. For this whole chunk, the acceleration is the same. But here, for this first piece, it's slowing down. Here, it's speeding up, going the other way. But the acceleration is constant the entire time. So down here, the object is speeding up, moving south. This particular chunk, from 4 seconds to 7 seconds, what's my object doing? Hold on, careful. What kind of graph is this? It's staying at a constant velocity. The velocity is negative 10 the whole time. This is not a position time graph, this is a velocity time graph. If my velocity is constant and non-zero, my object is moving. But it's moving at a constant rate. So my object is moving with constant velocity. And I'll just call that constant v. What's happening here? Okay, so here we've got an object that's slowing down. We also had, well, how do you know it's slowing down, Luis?
It's going south, but now it's going to north.
Right, so we have a negative velocity, which means that it has some speed and it's heading south. And we can see here that the velocity is going to start to creep up to 0. So my speed is decreasing to 0. So at this point right here, my object has stopped. So what does that curved line represent? This is a curved line on a VT graph. What do you think that means? What do you mean by rapidly? Yes, actually, Tristan. That is the right way to think about this. So if you think about this, the object is slowing down here, and the object is slowing down here at a constant rate. So my acceleration is constant for this chunk. Angel, you're good? Finished? Yeah, A block. And then head to foods. At least that's what I told her you were going to do. It sounds good. Here, on this VT graph, we know this thing is slowing down. But if you think back to the position time graph that I gave you before, the slope was equal to the velocity, so a curved line meant I had a changing velocity. Here, the slope represents acceleration. So a curved line means I have a changing acceleration. That's weird. My acceleration is not constant for this chunk of time. Acceleration is changing. Because this is a VT graph and slope represents acceleration, a curved line means my acceleration is changing. This is gross. Changing accelerations are not something you ever want to deal with. And if I'm not mistaken, and I don't think I am, this will be the only time in the next 2 years, if you take physics 12 and 11, that you're ever going to talk about changing accelerations. Because that is even, I'm even thinking about into my university career. We never talked about changing acceleration because it's weird. There is a name for a changing acceleration. Changing velocities means you're accelerating. Changing positions means you have velocity. Changing acceleration, does anyone know what that concept is called? I don't expect you to.
You feel like it's strange to think about it because, like, if you shouldn't change your acceleration, it's not increasing or decreasing. It's like just, I don't know how to explain.
Well, you're increasing your speed faster than you were increasing your speed before.
Yeah, it's strange.
But it is strange. There's a name for this.
Is it possible, like, to happen in real life?
Yeah. So, like, where you would deal with something like this. So let's say if we were going to really analyze the situation that this happened in, it's like a rocket launch. Because during a rocket launch, if you actually think about what's happening here, as the rocket gets launched, it's burning fuel. So the rocket itself is getting lighter the whole time it's burning fuel. So the acceleration isn't going to be constant. The acceleration is going to start accelerating faster and faster and faster, assuming those rocket engines are burning at the same rate, because as it's accelerating, it's also getting lighter. So the force is able to increase. We'll talk about forces in the next chapter. It's actually able to increase. So that's one example where as an object gets lighter, while it's changing its velocity, it's able to change its velocity faster. Before I take that question, I'm going to give you what this is called, a changing acceleration. That concept is actually called jerk. And you will never deal with this practically. I've never in my undergraduate physics career ever dealt with this. Sorry? if you're engineering, if you go engineering, you might deal with this concept of jerk, and it might, because there's real practical results that are involved there. But as far as what we do in physics, so much of it's theoretical, and we are always ignoring different things in physics. Like, well, we're going to look at some problems, and we're going to ignore air resistance. We're going to, when we talk about things being pulled by ropes, we're going to ignore the mass of the rope. Do ropes have mass? Yeah, they're heavy, but we're going to ignore that. As far as a lot of the other stuff that we talk about, objects, we're going to assume that they're spheres. We're also going to assume that those spheres are infinitely small, and we're going to talk about them as your center of mass. So we make a whole bunch of assumptions in physics anyway, and so concepts like jerk are just, we just brush it aside and don't talk about it. So a curved line like this would give a changing acceleration. So a tangent line on a curved section of a VT graph would give us what, do you think? Sorry? What kind of acceleration? On this kind of graph, if I drew a tangent line and found the slope of that tangent line, that gave me what? Starts with an I. Okay. Slope is velocity. So tangent line for my velocity is changing. The tangent line gave me instantaneous velocity, yeah? Velocity at that moment in time. We remember this, yes? You remember, or maybe if you don't remember it, you remember it happening to you? Maybe, sort of. So then what's this tangent line going to give us if the slope on a VT graph is velocity? Sorry, is acceleration. It's going to give us instantaneous acceleration. Good. I'm going to do that in a different color here.
Like in jerk, you can consider, for example, like somewhat like I'm gonna say like what's the name of the thing flying space?
A spaceship?
The space is like when it's going to another galaxy, like stops and goes to the speed of light, like a jerk, for example.
I don't know what to tell you. I don't know. The short answer is I don't know. Okay, so we've analyzed this. Now we're actually going to flip the page and do some calculations. We've seen it already. Some of you have identified it. If you're not seeing what your classmates were picking up, then I need you to accept the fact that average acceleration is found by taking the slope of a velocity time graph. We've seen this. Average acceleration is equal to a change in velocity over a change in time. So this is just, because velocity on the graph is the y-axis, this is just my rise. This is just a change in time. That's how my x value is changing on the graph. This is just my run. So that's going to give me slope here. Sorry? Yeah. Yeah. You just have to accept that this is happening. So we're going to, these calculations here, A, B, C, we're going to actually flip back, and we're going to do them on the previous, we're just going to do them right on the graph. So let's do that. I will make a note of which ones we want. So the first one we want here, I'm just going to make a note on the front just so we remember. We want the A, here the acceleration during the following times. We want 3 to 4 seconds, we want 4 to 7 seconds, and we want 0 to 4 seconds. Okay, so those are the time frames we want to deal with. So from 3 to 4 seconds, how is my object accelerating? Or what is the acceleration of my object for that entire chunk of time? Well, to solve that, we know it's slowing down and moving north, but here it stops, here it's for an instant, a brief moment in time, and then it starts to speed up the other way. And we said that the acceleration was constant because that line is straight. So we can figure out what that acceleration is. Acceleration is equal to a change in a velocity over a change in time. So this is going to be our rise over run. What is my velocity? And remember, change in is always a final minus an initial. So from 3 to 4 seconds, what's my final velocity? Let's go v final minus v initial over t final minus t initial. Let's actually write that in there. And then, I don't know if it was Khalil. Was it Khalil? Was it you? Did you just say it? Tanjut. V final is negative 10 minus our v initial. What's our initial v?
30.
It's 30. Our final time is? My initial time is 3 seconds. So I've got negative 10 minus 30. It's negative 40 over 1. So what's my, and this is meters per second. This one's in seconds. So then what's my slope there? Or what's my acceleration? Same thing. Negative 40 meters per second squared. This thing's accelerating rapidly. This is a substantial change in not a lot of time. Okay, so let's look at the 4 seconds to 7 second mark. What's happening in there? Do that a different color. That's that one. So let's do this one in orange. What's my acceleration for 4 to 7 seconds? Is it 0? Why is it 0? It's the same. We already we talked about this, or you, I can't remember who it was at this point. It might have been Zaid, it might have been Tristan, has already said that at this stage, my velocity hasn't changed. It's moving with constant v, which means my acceleration then must be 0. We could show that really easily using the same calculation we did before. My final velocity at 7 seconds, well, that's just negative 10. My initial minus my initial velocity of negative 10 divided by 3 seconds, yes. The 7 minus 4. Well, negative 10 minus negative 10 is 0. That's going to be the same thing as negative 10 plus 10. 0 over 3 is just 0. Jumping back and forth between thinking about it abstractly versus showing it mathematically concretely it can really be a struggle, and that's something I wanted you to recognize. That's why I wanted to go through this, talking about each of these things every step of the way before we actually did some of those calculations. Now the last chunk we're going to look at is the section here from 0 seconds to 4 seconds. What's my acceleration from 0 to 4 seconds? What is that even looking at? Sorry? That's what it's at. That's, if I remember right, that's what the question said. What is the average acceleration from 0 to 4? Sorry? So negative 20? How'd you do that?
The acceleration in 0 to 2 is 0. Oh, sorry. 0 to 3 is 0.
Careful. There's a procedure for finding average acceleration. You're trying to circumvent that procedure. Okay, so be careful how you think about it. Okay.
If that's 0 meters, if that acceleration is 0,
Yeah.
and then the other part is also negative 40,
Yeah.
add them and divide by 0. And divide by 2, you're at negative 20.
But why are you divide? Can you just nicely divide by 2?
That's a good question.
That's a good question, isn't it? Because you got to be careful how you think about averages now. because what you're doing is you're averaging a not a, yeah, it's not a, you gotta go back to, let's go back to the definition for acceleration. It's not a nice average like you had before, where you had, we can add up a bunch of things and divide by the number of things we added together. Because you're not just adding, because you said already here, we're not just adding two different accelerations together. Because those accelerations happen for different lengths of time.
Like the acceleration of 1 to 3 and 3 to 4, like make them together and divide by 2? Like
That's what Manuel wanted to do. And no, you cannot. Because they're not equal. I mean, let's go back to the definition. VF minus VI over T final minus T initial. You said you wanted to draw a line. What was the line you wanted to draw then?
From the beginning to final second.
So then this is what you're finding. Yes. That is the acceleration that we're looking for. It's not bad. It's not perfect, but it's not bad. So V final is -10 minus our V initial, which is 30. And how many seconds did that take? Took 4 seconds. So it's going to be -40 over 4, which is what? -10 meters per second squared. So if you're going to average it together, how do you have to think about, you, or if you're looking at wanting to do it Manuel's way and Luis's way, you two gentlemen, how do we have to think about, you have to add it like you're dealing with 4 seconds. So it's 4 different accelerations you're adding together. 0 plus 0 plus 0 plus -40 divided by the 4 seconds worth of time. So there's our set of average accelerations.
like you said,
Yeah, like Tristan described it. Yeah, you were right. Cool. Comments, questions, concerns?
oh, this was saying that I'm not just because I'm not in direction, so it's hard to see it, but after I'm going to see the video and
Works for me. Okay, so flip the page. The last piece here, we talked about it already. Instantaneous acceleration is found by taking the slope of a tangent line. Again, you are never likely never going to happen. Specifically instantaneous acceleration. It'll never show up. Unless you go into engineering and then all of a sudden it's going to smack you upside the face. But as far as the physics goes, we will do instantaneous velocity. Same concept, take a tangent line, find the slope. But you will not do instantaneous acceleration. So that's one thing that we can find off of our graph. The next thing, flip the page, is actually really interesting. We can use a velocity time graph to actually find our displacement. That's interesting. How? What is displacement?
the distance that you travel compared to your initial point.
Okay, so you can think of distance or displacement a couple ways. Distant or displacement rather, you can think of it as being a change in your position. How else can you find your displacement? Yeah? V times t. So your displacement could also be a velocity times a time. Well, isn't that interesting? What if I had something that I didn't give you any data for, I just gave you a graph and I said, well, let's find the displacement. What's happening here in this first chunk on the graph? We're going at I'm hearing it from the front 2 corners. We're going a constant 20 meters per second for how long? For 5 seconds. So I could use that information and I could say, well, d equals v times t. My v is 20. My v is 20. My t is 5. That's going to be what? What's my displacement going to be then? 100. 100 meters north. Because my units here are meters per second, and there's my direction. What did you just calculate? You calculated the displacement, but look at the graph. What concept of the graph did you just calculate? But yes, but what, look now we're dealing with, look at the shape. Connor. No. You found the area, right? This is a rectangle. The area of a rectangle is length times width. Here's my length. Here's my width. If you can see that, I'll zoom this in so maybe you can actually see what I'm writing on the color. There's a W. Here, I promise you there's a W there. And so all we did was the area of that space. Area equals length times width. Well, my length, that's just time. 5 seconds. Times my width, well, that's just 20 meters per second. 5 times 20 is 100. My seconds cancel out, so I'm left with meters. So what then must my area be? Well, it's got to be displacement, because that's the only thing we measure in meters. This then must be our displacement. And what that idea allows us to do, recognizing that the area under the line on a VT graph, it actually allows us to find displacements when our object's doing a bunch of weird stuff. So I could give you a scenario that looks like this. I could say, well, an object was moving at 20 meters per second for 5 seconds, and then it undergoes a uniform acceleration from 20 meters per second to 40 meters per second over 3 seconds. How far has the object gone in that entire time? You could do the kinematic calculations. You could say, okay, from this chunk it was this distance, and then for this chunk it was this distance because while it's accelerating. Or you could just graph the thing and find 3 areas. So we've done this first piece. What you need to recognize here is that for this chunk, the displacement while our object is doing what with a curved upwards line? It's accelerating. While it's accelerating, it's undergoing a change of position. So it's displacing. So when we've got this shape here, what you want to do is you want to recognize that this whole area is the one that we want to find. And the way to do that is by breaking this weird looking shape up into 2 shapes. The triangle up top and the rectangle down below. For this rectangle, what are these dimensions? So this is going to be 3 seconds, and this is going to be 20 meters per second. So for this chunk down here, the area is going to equal 3 seconds times 20 meters per second. It's going to be 60 meters. But we want to add that to this. Now that is, what shape is this? That is a triangle. What is the formula for the area of a triangle? That is the length of the hypotenuse. Nice try. What is the area of a triangle? Okay, one of you. Eric. Space times height divided by 2. Or I'm going to write it a different way here. It's 1/2 base times height. Which, if you've forgotten, I totally get, because I don't think you've done area like this since middle school. So if I'm judging you for not remembering that, it's only a tiny amount, so don't worry about it, but I am judging you a little bit.
You can do it, but
So it's a half base times height.
I'm questioning
What's my base for the triangle? So we're going to have 1/2 times 3. What's my height? It's rising from, yeah, you can't see it on here. It's going from 20 to 40. So that's going to be 20. So that's going to be 3 times 20 is 60. Divided by 2 is 30. This is seconds. This is meters per second. My seconds are going to cancel, leaving me with meters. So then my total displacement for this, for the 5 seconds to 8 seconds, 5 to 8 seconds, displacement is equal to what? Sorry? No, so the 5 to 8 seconds. It's just going to be just the 90 meters. But we could take this one step further and say, therefore, total displacement.
Is that what that one means, like the 3 dots?
Yes. You never seen that before?
No.
Okay, sometimes it shows up in math class. That's what these 3 dots mean, is therefore. It's a concluding statement. Therefore, total displacement from 0 to 8 seconds is going to equal the 90 meters from the 5 to the 8 plus the 100 meters from the 0 to 5. Gives 190 meters, and specifically which way? North. It's kind of cool. So, I told you that I could only derive 3 of those equations for you, and that I would have to wait until we looked at the graph to prove to you the other one. Oh, did I close my proof? I had my proof open. I totally did. That sucks. That's okay. Let's see if I can remember it. So, here's what we've got. I'm just going to slide this down here. Write down the proof or don't. It's entirely up to you. But for those of you who are like, where are these kinematic equations coming from? Where is our justification for it? I will show you the last one. So the equation that I'm trying to prove to you is this one here. D equals VIT plus 1/2 AT squared. Sorry, I'm going to zoom this in a little bit so you can see what's going on here. We're seeing some of it already. This VIT piece is a constant velocity plus a length of time. So this VIT piece, looking just at this section of the graph, this chunk here represents this bottom piece on the graph. Well, that's cool. We like that. What about this half AT piece? Well, for constant acceleration, which is all that you guys are ever going to deal with, for constant acceleration, we know that the acceleration is equal to the slope here, and the slope's going to be constant. So I've got a sloped up line. So the shape is always going to be a triangle. That's where this half piece is coming from, because the area of a triangle is half AT squared. But if we look at what I did here, I multiplied my time by our velocity. Well, how does a time times a velocity equal an acceleration times time squared? That's weird. What's going on there? Well, I didn't multiply it by a velocity. I multiplied it by what? This 20 doesn't represent the velocity. It represents what? Nope. How did I get 20? The length of what? No, it's not the length. It was the area, right? Half base times height. So that 20 came from the height of our triangle, yes? How did I find the height of that triangle? And doing what with those values? I subtracted them. I took my final velocity, subtracted my initial velocity, and I got my change in velocity. It's kind of cool. What did I do here? This was a change in time. So I took my velocity and I multiplied it by a time. Interesting. That's still not a times t squared. Here I'm going to have to do a little bit of maneuvering for you. So take a look at this. A is equal to what? A acceleration is equal to a change in velocity over a change in time. So if I multiply our acceleration by a change in time, that's going to give me what? Acceleration times a change in time, that is a change in velocity. Yes? Are you cool with that idea? Acceleration times time is equal to a change in velocity. If I'm accelerating for a length of time, I'm changing my speed. What happens if I do that again? I take my velocity and I multiply that by a length of time. What have I found? Velocity times time is? I heard it back there. It's a displacement, yeah. But I have to do that to both sides of my equation. This over here, delta v times delta t, that's just d. Which means an acceleration times my change in time squared is going to give me a displacement as well. So what I've got here is I've got one form of displacement plus another form of displacement gives me my total displacement, which is exactly what we did here. I had one chunk of my displacement plus another chunk of my displacement equals my total displacement. And that's where this equation up here comes from. That kind of larger, nastier kinematic equation comes from the graphical analysis of a velocity time graph. For those of you that cared, there it is. For those of you who had no desire of knowing where it came from, you just want to know how to use it, forget that the last 5 minutes just happened. Yeah, Manuel. Yes, I'll post that to the Google Classroom. Absolutely. You missed that yesterday. No, it's not that Santa Claus is real. It's that if he was real, he is dead. That's the one I said the proof was. Okay.
Santa Claus is exactly.
Let's talk about this though first. There is, okay guys, I know there's only a little bit of time left. There is a relationship I want you to see, and I'm going to give you some homework. The relationship I want you to see is this. We can move back and forth now between these graphs. Okay? From velocity, the area under the graph gives me displacement. From velocity, the slope can give me acceleration. Which means by analyzing these different graphs, we can generate subsequent graphs, which is kind of awesome. And you're going to hate it, but we're going to do it. So like, let's look at this one. I had a curved graph on my displacement time graph. What does that mean? Curved displacement means my velocity, I have a positive velocity and it's changing. So it means I have to have an acceleration. What is so that's going to look like a straight line going upwards on a velocity graph. This thing is accelerating, which means I have a constant positive slope. So then I could theoretically graph my acceleration. Well, this is just going to be a constant value, yes? So then the graph of a constant value is just going to be a straight flat line on an acceleration time graph. What if I had something that looks like this? Let's do another one. What if I had that? This is D, that's V, that's A. The bottoms are all T. What's this? On a DT graph, what does that line mean? A constantly changing, no. On a DT graph, a straight line means I have a constantly changing position. If my position is changing constantly, that means what is constant? No. Well, yes, but no. But yes, we'll see that in a second. It means my velocity is constant. What does a constant velocity look like on a VT graph? A horizontal, because this line's straight. Straight, flat line. Which means, what's my acceleration here? You're right, Luis, it's constant, and it's, so it's going to look like this. Let's do one more. Oh, the bell's going to go while we're doing it. That's okay. We're doing it anyway. Bell goes, don't move. What if I have this? That's D. That's V. Finish this. Bell's going to go. That's okay. Do it anyway. What's happening? Oh, I got 4 minutes. Never mind. Bell's not going to go. What's happening here? The displacement's decreasing. And it's doing what? And my velocity is increasing because this line's getting steeper. Which means it's, I heard it back there. Eric, was that you? Canor? Go. It's accelerating, yeah, because I'm going to have an increasing velocity. So what is this going to look like on a VT graph? My velocity is going to start where? My velocity is going to start where? Velocity represents the slope of a graph. What's this one look like? What's the slope? What's the slope of a flat line? 0. And then what's happening to it? It's getting more and more negative. That's weird. So what's happening here? My VT graph is going to look like what? It's going to go that way. Because it's getting negative. So then what's my acceleration graph going to look like? This straight line is, which means it's accelerating, and it's accelerating negatively and constantly. So my acceleration time graph is going to be flat because it's constant acceleration, but it's going to be where? Somewhere negative. It's going to look like that. Interesting, eh? It's good. What I want you guys to look at, this page here, both sides. How do we do that? Yeah, how dare I? Yeah, this one is two-sided.
Oh, great.
Do I want you to do this one?
Yeah.
No, no.
Hang on.
Actually,
Both sides of that first one.
Both sides of this first one. Well, skipping class is worse. Skipping class means you got to catch this up on your own time.
And then what?
Um,
How about let's do it even? 2, 4,
No,
and 6.
no, no. Good enough.
I want you guys on this page here. I want you to try 1,
And that's it.
and I want you to try. Actually, you know what? We'll jump in. We'll jump in. Do 1, try 1, and we're gonna spend Monday going through some more of this. Yeah, try 1. This page, both sides. Manuel, as you don't walk away from me until I dismiss you. This page, both sides, and then I want you to try number 1 here. If you don't have any graph paper at home, hold off on 1. 1 will give you a head start for what we're going to do on Monday. Have a great day, guys. We'll see you later. You betcha.
How we doing with this?
See you later. Yeah, you too, Tristan. Day is limited. Bye. Okay. Okay, so there's that, and there's that, and we're done.